Hello everyone, I hope you're doing well. Today we're going to continue our discussion on Lewis structures, but we're going to expand on that a little bit and talk about three-dimensional shapes of molecules. Now, part of the reason that we care about the shapes of different molecules is we can then determine how molecules are going to interact with each other. So for instance, maybe if a molecule is super bulky, then it's not going to react with another molecule that well. Or maybe if a molecule is really tiny and has a very simple shape, it could react very quickly and easily. But additionally, we'll talk about tomorrow polarity of molecules, and that is dependent on the shape of molecules. So shapes are really important for different molecules. And we can determine the shape of a molecule from its Lewis structure. So remember last time we went over a few examples of Lewis structures. And so now we're going to talk about their shapes. So most molecules and polyatomic ions are not flat two-dimensional objects. Most have distinct three-dimensional shapes. Now, we're including polyatomic ions here because remember, they have a group of covalently bonded atoms. But the difference between a molecule and a polyatomic ion is polyatomic ions have a net charge. But they do still have a three-dimensional shape that we need to take into account. Now, the shapes of molecules, or polyatomic ions, can be predicted using a theory called the valence shell electron pair repulsion theory, which is a very long name, so we tend to use the acronym VSEPR, but we pronounce it VESPER, so we call it the VESPER theory. And the main idea behind this theory is that pairs of electrons want to be as far away from each other as possible. Or another way to think of that is atoms with surrounding electrons want to be as far away from each other as possible within a molecule. So down below we have three different types of shapes that are pretty common in different molecules. The first one is a linear shape, which is pretty self-explanatory. One example of a linear molecule is CO2. So you might remember from our last lecture, we went over the Lewis structure of CO2, carbon dioxide. And we're going to consider the oxygens as electron groups or pairs. And then we're considering the carbon in the middle as kind of our reference point. So here we're listed that we have two electron pairs, and those are the oxygen atoms in this particular example. And those want to be as far apart from each other as possible. So the angle between those two oxygens is 180 degrees. All right, now there's also something called trigonal planar. And this refers to something that has three electron groups. So one example is SO2, and we didn't go over SO2's Lewis structure, but it would look like this. So SO2 has two oxygens, one on either side of the sulfur, and a lone pair of electrons. So we're going to count the two oxygens and the lone pair of electrons as electron pairs. So we have oxygen atoms and a lone pair of electrons. So those are our 3 electron pair groups. And they want to be as far apart from each other as well. So in actuality, we get something that kind of looks like this, where those oxygens are far apart from this lone pair, and I'm going to draw a little bubble around it to kind of show it as a group. So these are pretty far apart, these are pretty far apart, and then these are also far apart from each other. So it kind of looks like a triangle. But the name comes from the fact that we have 3 groups, so trigonal, or sometimes you'll hear it as trigonal. And then planar refers to the fact that all of these bonds are in the same plane. So they're kind of just sitting flat on a piece of paper almost. And then in our last example, we have a molecule that has a tetrahedral shape. So this example, NH3, we have 4 electron pair groups. So there are 3 hydrogen atoms, and there's actually a lone pair of electrons in there as well. And we'll probably go over this later, so I want to leave that a bit of a mystery for now. All right, so according to this VSEPR theory, again, electron pairs in the valence shell of an atom are going to repel each other and get as far away from each other as possible. So down below we have the example of SO3. So again, you'll notice that there are these lone pairs on each atom. Those are what want to be as far apart from each other as possible. So these 2 oxygens want to be really far apart, and these 2 oxygens want to be really far apart from each other. So when the theory is applied to the valence shell electron pairs of the central atom in a molecule or ion, the shape of the molecule can be predicted. Now, a central atom is an atom that is bonded to other surrounding atoms, such as the sulfur atom in the SO3 molecule. So this sulfur atom is our central atom, and that's kind of what we're basing everything off of. So sulfur has 3 electron groups bonded to it, and those are all oxygen atoms. And again, they want to be as far apart from each other as possible, so they're going to spread out from each other. And we almost form a triangle here. So this would also be trigonal planar, similar to our SO2 example. But in this example, sulfur does not have a lone pair. It has 3 oxygens. All right, now there are a few rules for VSEPR theory. So rule 1, all valence shell electron pairs around the central atom are counted equally, regardless of whether they are bonding or non-bonding pairs. So remember with SO2, we had bonding atoms, which were the oxygen atoms, but then we also had a non-bonding pair of electrons, which was our lone pair. So that's what they mean when they refer to non-bonding pairs of electrons. So we're going to count all of those equally. So we're just going to refer to each of those as electron groups. And then in rule 2, double or triple bonds between surrounding atoms and the central atom are treated like a single pair of electrons when shapes are predicted. So when we were looking at SO3, we had a double bond and then two single bonds. But we're going to treat all of those bonds equally. So the double bond does not get special treatment. It's going to be treated as if it's just one group. And then down below we have some nice figures of our three different geometries that we're interested in. So you can think of each electron group as a balloon. Now, if we tied two balloons together, they're going to form a linear molecule. If we tied three balloons together, they're going to form a triangle. And if we tie four balloons together, we get what's called a tetrahedron. And so that kind of looks like a pyramid almost. Okay, so the Vesper theory can be applied to molecules or ions that have up to 6 pairs of electrons around the central atom, or 6 electron groups. But this discussion will be limited to molecules with no more than 4 pairs. So don't worry about any geometries beyond the 3 that we talked about, which are shown below. Those are the only 3 we're going to focus on in this class. All right, so now for electron pair arrangements. According to Vesper theory, the arrangement of electron pairs depends on the number of electron pairs. So this is what we were discussing earlier. Again, we have a linear structure where E is the central atom. And then we have 2 groups, one on each side, and they're going to be as far apart as possible. So they actually will form a 180-degree angle. And then if we have 3 pairs of electrons around the central atom, that's going to form a flat triangle, which we said was called trigonal planar. And the angle between each of these groups is 120 degrees. So between the top and the bottom, those are all 120 degrees. And then if we have 4 pairs, those are going to be located at the 4 corners of a shape called a tetrahedron. And so this we said was called tetrahedral. And the angles between each of those groups will be 109.5 degrees. So kind of a specific angle, but that will be our angle there. And again, these are the only 3 geometries that you have to know for this particular class. All right, so let's draw a Lewis structure and determine the shape of the molecule for CO2. So we kind of already went over this in a previous lecture, but we'll go over it again. And remember that when we're drawing the Lewis structure, we want to first determine which atom goes in the middle. So in this case, carbon can form the most bonds. So it could form 4 bonds. But additionally, it's by itself. So that tells us it will be in the middle. And then we're going to place an oxygen atom on either side. And then we want to count how many valence electrons we have for this molecule. So we have 4 valence electrons for carbon. And then we have 6 valence electrons for each oxygen. So we'll multiply 2 by 6. So that gives us a total of 16 valence electrons. And next we're going to start forming some bonds between carbon and each oxygen. So that means we used up 4 valence electrons. So now we have 12 valence electrons left. And we want to make sure that each atom has 8 valence electrons according to the octet rule. But I usually start by putting octets around the outside atoms first, and then I move electrons around later if I need to. So we'll start by putting some lone pairs on each oxygen. So we just added 2, 4, 6 electrons to the oxygen on the right, and now we're going to add 2, 4, 6 electrons on the oxygen on the left. So we used up all of our electrons, and both oxygens are happy. They each have 8 electrons, but carbon only has 4 electrons. So we're going to actually move electron pairs down from each oxygen so that we can give carbon 8 total electrons. So I'm just going to erase the lone pairs on the top and just move them down so that they're shared between carbon and each oxygen. So now carbon has 8 electrons, and each oxygen still has 8 electrons as well. They're just sharing more of their electrons with carbon. Now we can draw this as double bonds. So we'll have 2 lines there, which each represent 2 electrons. And that will be our Lewis structure for CO2. Okay, so now for the next part, we need to determine the shape of the molecule. So if carbon is our central atom, so we'll just write E for central atom. We have, I'm just going to draw balloons. We have a balloon on the right and a balloon on the left. So that would be which shape? So hopefully you said linear, and we actually talked about this earlier, so. All right, so that would be a linear molecule. Now, another quick question, what is the angle between those 2 oxygens? So hopefully you said 180 degrees, so they are 180 degrees apart from each other. So that's this angle here. All right, and then here is another solution slide, so it kind of goes over the same thing we already talked about. A couple things to remember. The central carbon atom is surrounded by 2 double bonds. Remember that each double bond counts as a single electron pair or an electron group. So really we're going to treat those double bonds as almost single bonds when we're trying to determine the electron or the geometry. Okay, let's do another example. Let's go over NH3. So first we're going to draw the Lewis structure. And nitrogen is by itself, and it can make the most bonds out of nitrogen and hydrogen. So nitrogen will go in the middle. And then we'll just surround it with some hydrogens here, and we have 3 of them. Now let's determine the number of valence electrons for this molecule. So nitrogen is in group 5A, so it has 5 valence electrons. And then each hydrogen has one valence electron, so we're going to multiply 3 by one valence electron since we have 3 hydrogen atoms. And that should give us a total of 8 valence electrons. Now, in the next step, we're going to start making some bonds between nitrogen and each hydrogen. So we used 6 electrons to make those bonds, which means we have 2 electrons left. So then the question becomes, where do those electrons go? Now, each hydrogen, remember, only needs 2 electrons to be happy. It doesn't actually need an octet like other atoms do. So if each hydrogen is happy, let's look at nitrogen. So nitrogen only has 2, 4, 6 electrons, and it would like 2 more to have 8. So we can put that extra set of electrons on nitrogen. All right, so this is our Lewis structure, and we can also draw this with lines instead of electrons between each of the atoms. But we are going to still represent lone pairs of electrons as 2 dots. So we're not going to represent that as a line. Okay, so if we now know the Lewis structure, we can determine the geometry or the shape. All right, so remember that we're going to treat bonding and non-bonding electrons the same. So we do have 3 bonded hydrogens and then 1 lone pair of electrons. So if we were to draw those as balloons, I don't know if this quite makes sense, but we do have 4 total groups surrounding nitrogen. So what shape would this molecule have? So hopefully you said tetrahedral. So remember, this looks like a pyramid that has 4 corners. So we've got our top corner and 3 bottom corners. All right, and then second question, what is the angle between each of those electron groups? So remember, this is the really specific angle. So this would be 109.5 degrees. And that's between each of the corners there. Or another way of thinking about it is between each of the different electron groups. And then here's a solution slide if you want to look at that later. And let's do just one more example. This time we're going to draw the Lewis structure and determine the shape of BF3. And this is called boron trifluoride. Okay. So in this instance, we have boron and fluorine, and boron is by itself, so it likely goes in the middle. And then we're just going to surround that with our fluorine atoms. And now let's figure out how many total valence electrons we have. So boron, if you look at a periodic table, is in group 3A. So that means it has 3 valence electrons. And then fluorine is in group 7A, so it has 7 valence electrons, and there are 3 fluorines. So we'll multiply 3 by 7. All right, so 3 times 7 is 21. and then we add 3, so that gives us 24 valence electrons for this molecule. So now we're going to start making some bonds between boron and each of the fluorines. So we've used up 6 valence electrons, and that means we have 18 valence electrons left. So now let's give each fluorine an octet. So we're going to add 2, 4, 6 electrons to the first fluorine, and then 2, 4, 6 electrons to the second fluorine, and 2, 4, 6 electrons to the last fluorine. All right, so now each fluorine has 8 electrons. Now, boron only has 6 electrons, but this is kind of a tricky thing. Boron only needs 6 electrons. So it also doesn't need an octet. It's kind of similar to hydrogen, except boron is perfectly okay having 6 electrons. And part of the reason for that is if we look at the Lewis symbol for boron, it has 3 valence electrons, so it's okay just making 3 bonds. It doesn't really need to make any more than that, and in some instances boron will take on more electrons, but it's happy just having 6. So this is another one of our exceptions. So for this particular molecule, we now have the Lewis structure, and we can see that boron only has 3 groups. So which shape would BF3 have? So hopefully you said trigonal planar. So these balloons down here, I'll actually redraw these so that they're in the right shape. So these would be more so like this, where they're all 120 degrees apart. Okay, so I think we'll stop there today. I'll post some helpful worksheets for working through shapes of molecules and also for Lewis structures, so you can get some more practice with that. And then we have one more topic to cover in Chapter 4, and then we'll move on to Chapter 5. So I will see you in the next video.